This is a GCSE video about magnetism. Now, most of us have seen magnets, and often they look like this. They're given specific colours to indicate which end is which. And we know that when we bring two magnets together, they either attract each other or they repel. Okay, and that force there that's pushing that other magnet away is called repulsion or repelling. So we've got two properties there. We've got attraction, which is when things want to be together, and we've got repulsion, which is when things try to be apart. So here we say one magnet attracts the other, and here we say one magnet repels the other. And if we look carefully at the colours, we can see what happens when we have opposites attract and the same sides repel. So we say that like poles repel. These the different ends of a magnet are called the poles. So like poles repel, and unlike poles attract. So now the reason that happens is because around a magnet there is something called a magnetic field. Now, a magnet has two poles. Here on this magnet they're coloured red and blue, but we give them the names North and South Pole. So I'm going to put the North Pole there and the South Pole there. Now, just like our Earth is a giant magnet, so we have a North Pole and a South Pole on Earth as well. And the way that we describe a magnetic field is by saying, well, what would happen to a North Pole? What force would a North Pole experience anywhere near this magnet? And if you do an experiment like putting a compass around here, the compass will point in the direction that the force is acting. And so what we see is this. What we see is this. Now, anywhere here you can see the arrows are pointing towards the South Pole, because the force is what happens to a North Pole, and we know that North Poles repel other North Poles, so the North Pole is going to be pushed away from this North Pole and be attracted by the South Pole. So arrows always point from north to south, and on a bar magnet they go round like this. And I could draw more. There's not just two of them, there's lots and lots of different lines that we could draw, but this is generally the pattern of the magnetic field around a bar magnet. And so if we bring another bar magnet here and we find the North Pole and we put the North Pole here, if we keep that one if we keep that one steady, then we see that the force acting on this North Pole here takes it to the South Pole. Same if we put this here, the force acting on this North Pole here makes it follow these lines. So we know that the magnetic field around a bar magnet looks like this. Now, something else that you might have noticed about magnets is that if you bring a magnet close to something that is made of iron, like this, the iron is attracted to the magnet. Now, in that particular case, I was bringing the red side, the North Pole, close. If I do the same with the South Pole, they're not repelled, they're attracted just the same. So the reason for that is that these nails aren't magnets on their own. If we bring those two nails close together, they don't attract each other, they don't repel each other. So the nails are not magnets, only this is the magnet. And what is happening in the nails is we are inducing magnetism. Now what that means is, when we bring a magnet close to anything made of iron, it very temporarily, while the magnet is around, and only while the magnet is around, it turns into a little magnet. And when we remove the magnet, the magnetism is removed and these nails are no longer magnets. Now, to explain why that happens, we have to look a little bit closer inside the structure of these magnets. So inside, a magnet is made up of lots and lots of what we call grains within the metal. They kind of stack up together like this. Now, each one of those grains has a certain magnetism. It has an orientation. So I'll draw those with an arrow here. This is what the grains look like in a magnet. They're all pointing the same way, and so there is the same magnetism, the same field is created by each one of these grains. And so on a bigger scale, all of the grains combine together to make a magnet, a permanent magnet. Now, inside the nails, the grains look more like this. They're all pointing in random directions, and when we bring the magnet close, they all start to point at the magnet. They all turn and they start to point at the magnet. So temporarily, the nail turns into a magnet. When we remove that magnet, all of those grains start to point random directions again. So when we're talking about inducing magnetism, what we're doing is we're turning all of the small grains of magnetic material inside this iron nail, and we're making them all face the same way. So it very temporarily turns into a mini magnet. Now what we call that is a soft magnetic material. And iron is a very good example of a soft magnetic material. Well, soft means that it can get a magnetic field very quickly, very easily. All you need to do is move it close to a magnet. But then, once you remove the magnet, all the magnetism leaves again. So soft means it can gain a magnetic field quickly, it can have induced magnetism, but then it loses that magnetic field very quickly as well. That is very useful for electromagnets. When we turn the switch on, the magnet turns on. When we turn the switch off, it doesn't stay as a magnet, it stops being a magnet. So a soft magnetic material like iron is very good for electromagnets. Now going back to this one, this is our permanent magnet. When we remove the magnetic field from this one, there's no other magnet around here. We've removed the magnetic field, but this is still a magnet. So this is not a soft magnetic material, this is a hard magnetic material. And steel, which is what this magnet is made from, is a good example of a hard magnetic material. It's difficult to turn into a magnet, but once it is a magnet, it's very hard to make it stop being a magnet. You can't just move it away from the magnetic field. It stays as a magnet. So, you've got a soft magnetic material which is easy to change into a magnet, but then it loses its magnetism very quickly. And you've got a hard magnetic material which is hard to make all those grains align, hard to turn it into a magnet, but once it is a magnet, it stays as a magnet. What that means is that steel is used for making permanent magnets like this, and iron is used for making electromagnets, which need to be switched on and then switched off. This final section of this video is only for triple IGCSE students, so if you are not studying triple IGCSE, you can switch off now. Triple students, you need to know how to make a permanent magnet and how to demagnetize it afterwards. So remember that in a permanent magnet, or in any kind of magnetic material, there are grains. I'm going to draw them a little bit more simply than I did last time, like this. And what you need to remember about making a magnet or destroying a magnet is that a magnet has all of these grains pointing in the same direction. The magnetic field of the grains is all pointing in the same direction. And in an unmagnetized material, they're all pointing in random directions, so they cancel each other out. Now, in order to make those grains line up, we can do one of three things. First of all, we can use another magnet to stroke like this the material, and gradually that stroking with the magnet attracts all of these poles, all of these magnetic fields in the grains, and they slowly all start to move and point the same direction. So they move and they're all starting to point the same direction because we're stroking it with a magnet. So that's one way we can make a magnet, is by moving another magnet along the length of the thing that we're trying to turn into a magnet, and that moves all of those grains to pointing in the same direction. The second way that we can do that is by putting it in a magnetic field, putting that material in a magnetic field, and then hammering it. And what hammering does is it shocks these, the grains get a little moment to move around, it gives them kinetic energy so they can move around, and gradually, as we keep hitting, the grains start to move around, and because they're inside a magnetic field, they all start to point in the same direction, because as they're moving, they're being attracted by that magnetic field, so then they all start to point in the same direction. The third way that you can do it is you can use electricity, and as we will learn about in the following videos, electricity also creates a magnetic field. So if we put this material inside a coil with a DC voltage, a direct current, so it's only in one direction, then it will slowly turn into a magnet. So those are the three ways of making a magnet, and those are the same as removing that magnetism. You can hammer it with no magnetic field around, which starts to move the grains and they start to point in opposite directions. You can heat it up, and heating it up gives these grains enough energy to move around and face opposite directions to each other. And also you can use alternating current in a coil. An alternating current, remember, is changing directions all the time, and so the alternating current starts to move some of the grains and leaves others pointing that way. And so you can demagnetize a material in any of those three ways by getting the arrows to point in opposite directions.